strive, but few endure. There are many who struggle, but few prevail. And of those who remain, there is only one who can truly be called a hero.
I'm Jorge Ribas, and you're wondering. Before we begin, let's take a quick stroll through the Cyborg Hall of Fame. You'll see heroes, villains, cops, Lando Calrissian's best friend, California governors, and guys worth $6 million. And while the idea of melding man and machine is firmly rooted in science fiction, the technology to tap into our brainwaves to access computers or move prosthetic limbs is very real and already helping people. People like Marjorie Nye, who is in the early stages of cerebellar ataxia, a neurodegenerative disorder that can affect a person's motor skills, speech, and vision.
The cerebellum basically controls the smooth movement of things in your body, so when that's degenerating, it can cause all kinds of little quirks.
Quirks that can make a simple task like picking up a glass of water near impossible.
Let's say she wants to play a computer game on a joystick, but when she reaches out a joystick, she cannot target it properly. Well, now why not create this sort of brain-machine interface to take over the function of a joystick?
In essence, building an external cerebellum that would compensate for a disease or loss of a limb. During the experiment, Nye wears a cap that measures her electroencephalogram output, or simply, her brainwaves. These brainwaves are then fed into a computer. Researchers look for slight modifications in the frequency and then translate that into a specific command. In this case, it's pushing a ball up and down in a Pong-like video game, as well as opening and closing a prosthetic hand. So it's not just like imagining, like I can imagine myself moving my left hand, but it's more than that.
Yes. Like sometimes if I'm having trouble doing it and I really think, man, I just wish I could reach out there and push it down, then it actually goes down because I'm having a more concrete, like physical kind of thought.
Since the cap is just resting on the top of Nye's head, the brainwaves aren't that clear. That presents a challenge to doing more advanced things.
The signals recorded from the scalp are very noisy and fuzzy. Signals recorded from the brain itself are more specific. Signals recorded from brain inside the brain by putting tiny microelectrode are going to be very specific. But those are invasive.
And that's where these guys come in. They're developing control strategies for next-generation prosthetic limbs by using those more invasive methods.
This hand right now is capable of essentially two independent actuations. So one is that there'll be a central motor that can bring all 5 digits together, and then there's a separate actuation of the thumb.
By going deeper into a subject's brain, in this case a macaque monkey, they're able to record neurons firing off for specific motor movements.
And what we're doing now is that we can sort of play back that neural data, develop algorithms here locally at Hopkins, and then be able to see whether we can use that signal to control a hand.
So that means that this robotic hand is now moving based on something a monkey once did. And it's intuitive enough that it can pick up anything from a tennis ball to car keys.
But we want to take it further, right? We want to be able to do much more dexterous movements, like moving your individual fingers, rotating your wrist. And for that, it's not clear right now whether it'll be something that's intuitive, whether you could just think of grasping your hand and there'll be a known signature for that, or something where it's going to require a little bit more training or more advanced signal processing algorithms.
For Discovery News, I'm Jorge Ribas.